just the big word is what scares people. Right? Everyone's back? Yeah. So the juxtaglomerular apparatus. Can you say that very fast? No. It's also referred to as the JGA. Don't let the word scare you. Juxta means next to, and you'll see this word. You'll also see it as juxtamedullary nephrons, meaning that the nephrons themselves are very close to the medulla. So you'll see these kind of words throughout nephrology. So juxta means next to the glomerulus. So it's not the glomerulus, it's next to the glomerulus. What we're talking about is an area that's right over here. And what this is going to be dealing with, remember how we talked about earlier, that the DCT has to fine-tune things. It has to put things back into the bloodstream, but how does it know how much to put back or how much to take away? The only way it can do that is that it somehow needs to communicate and understand what the contents are of the blood vessels. So this DCT is going to touch the blood vessel. And how this all happens is that it gets all, as you've seen with my pictures before, it gets all squished together, and the way it's set up is that this DC is actually touching the afferent arteriole. Okay? So what you're looking at is if the DCT comes out of the board, you have a DCT that's going to be touching. So here's a cross section of a DCT. And it's touching the afferent arteriole. And that's what we're talking about. It's an apparatus that's next to the glomerulus. And that's in all your models. So this is where the DCT lies against the afferent arteriole. So I'm going to draw it over here so you can see it a little bit better. This is a cross section of a afferent arteriole. Now don't draw it with me because I'm going to be erasing some stuff and changing it, and it'll get you frustrated, and people usually throw tomatoes at me like, I just drew that and you're erasing things. So let me just finish up over here and you'll see what this is. So this is going to be your afferent arteriole. So afferent arteriole, not artery, arteriole. And that's going to ride alongside a DCT. So this is a DCT. And there's simple cuboidal epithelium here. Okay? Now, the cells of the afferent arteriole that are touching the DCT, they get modified. This is where I'm erasing stuff. They change. And these cells are now referred to as the juxtaglomerular cells, or the JG cells. The cells of the DCT that are touching the JG cells, they also get modified a bit. And these cells are referred to as the Macula Densa. This whole thing is called the Juxtaglomerular Apparatus. In the JG cells, inside the cells, they have granules that contain an enzyme slash hormone called renin. You learned about renin a few chapters ago, probably in endocrinology and also circulation. So now we got to talk about how the mechanism, what's going to make this renin come out. The JG cells have the renin. So this is what's happening here, so you can appreciate it a little more. There's the Bowman's capsule, PCT, loop of Henle, DCT. Here's the afferent arterial, glomerulus, efferent arterial. This is where it's touching, and there's a close-up of it. Okay? Similar to here. Here's a DCT. Here's the afferent arterial. You'll have JG cells here. Macula Densa over here. You also see it here. Whoop. All right. Here's the, and you'll see when you get closer, but there's the afferent arterial. Here's a DCT coming up. The DCT's touching the afferent arterial. Macula densas of the DCT. JG cells of the afferent arterial. So then what does this have to be? What is this? Efferent. Yeah, that's the efferent arterial. Okay? So all of this is fair game for your practical exam. Okay? Let alone your lecture. One other thing I forgot to show you before is this model here, which looks busy, but it's not bad when you get up close. You definitely can't see it in the back, but it looks busy. But what's happening here is that you have these green balls. These are your Bowman's capsules or renal corpuscle. Okay? You'll find the orange coming out of them. There's your PCT. If you follow it, it'll go down. There's your loops of Henle. And then they start bending and shaping over here. There's your DCT, and they dump into the collecting ducts. Okay? I could point to things on here. What is this? What is that? What's the function of this? What hormone targets this yellow? What hormone targets mostly where the purple is? So that's all fair game from all the stuff we've been talking about. Okay? So I'll try it. Okay. So far, so good? All right. Now, we got to talk about, and this will help you for lecture 2. It drives students nuts, so I'll take advantage of it and do it in here. What makes the renin come out? How does this communication talk here? All right. The JG cells, the juxtaglomerular cells. They're part of the afferent arteriole. They're the enlarged smooth muscle cells of it, and they have these granules that contain renin. Now, they act as mechanical receptors or baroreceptors. And what that's from nervous system, okay? The different receptors. Baro, think of a barometer. A barometer assesses atmospheric pressure. So this is going to assess pressure. What pressure? Blood pressure. Okay? So this is going to sense blood pressure. Well, how it comes to be. When you have a decrease of blood pressure in the afferent arteriole, it's going to tell the JG cells to release renin. Renin goes through a series of events that you should have learned from before that's going to increase blood pressure. Okay? So the JG cells are mechanical or baroreceptors that sense low blood pressure. If the blood pressure is low, then renin comes out of JG cells directly. and then it's going to do a series of events to get the blood pressure back up. Okay? That's the easy part. Now, the macula densa, we have a couple indirect things. This is what drives the students a little bit wild. These are part of the DCTs. They lie adjacent to the JG cells of the afferent arteriole. And these function as chemoreceptors and osmoreceptors. Chemoreceptors, it senses a certain item, sodium or potassium, something. That's what a chemoreceptor is. It senses something, some chemical. Osmoreceptors, it senses the concentration of something. So the macula densa act as a chemoreceptor. It's going to sense a certain chemical, and it acts as a osmoreceptor, which is going to sense a certain concentration. As opposed to the JG cells, they act as mechanical or baroreceptors. They sense pressure. Okay? So here's another way that renin can be released. I'll go slower with you to make you understand this. Okay? When the blood pressure is low, we need to release renin. Now this is one way, but we need to amplify it. Now the only way you can really understand it, I'm going to draw something over here that you can appreciate this a little bit better. And I'm going to draw it a little bit different, but I think you'll understand the concept. You see what I drew here? Bowman's capsule, the glomerulus, afferent, efferent arterioles. What is this? PCT. See, you learned a lot of stuff here. Okay. Now, the best way I can explain this to you, well, let me also, before I get into that, let me explain to you that the filtrate goes through here. How fast the filtrate goes through here is something called a GFR, a glomerular filtration rate. How fast is the filtrate going into the Bowman's capsule, entering the nephron over here? All right, how fast is your car going? 35 miles per hour, 100 miles per hour. That's what's happening here, but it's I think it's cc's per second kind of thing. All right, so it's the rate. We call it a glomerular filtration rate, and you'll see that quite often. Okay. Now, for you to understand this, I'm going to make this really simple. Really simple. Think of a little monkey over here. Now, I don't draw, as you know, I don't really draw things very well when it comes to animals and humans. It's supposed to be a monkey. Let's make this face. Better? Okay, well, you get the picture. All right, so you have this monkey over here, and let's say what's coming through here is bananas. All right, that's what the filtrate is in my scenario. Okay, it's water, it's amino acids, all that stuff. But you're going to have bananas coming through here. How fast the bananas are coming through into the nephron is the glomerular filtration rate. Okay? Now, so far so good? Okay. Now, for some reason, the blood pressure goes down. When the blood pressure goes down, then what is the GFR going to do? Is it going to go faster? Is the bananas going to come in here faster if the blood pressure is low? Or are they going to go slower? Slow. Good. So let me ask you this. If they're moving slower, the job of this monkey is at the PCT. He's the one that's going to be reabsorbing. He's picking up the bananas. So if the bananas are moving slower do you think he could pick up more bananas or less? They're moving slower now. More. Does that make sense? If they're going fast, it's like, geez, I can't, the picture that come into my head, I don't know if you know I Love Lucy, but the chocolate factory, it's going very fast. It's a classic thing. Well, in this case, they're moving very slow. So as one's here, he's able to pick it up. Another one, he's not missing any. Does that make sense? So let me ask you this. If the blood pressure is lower, would you have more reabsorption at the PCT or less? More. So instead of 65%, maybe it's 75%. You see how you're understanding this? So what's going to happen here is that if you decrease the blood pressure, the GFR decreases, which means there's a less flow into the nephron, which means you're going to increase reabsorption at the PCT, all right, in the first part of loop of Penley, okay? Does that make sense so far? So then, what's the concentration going to be like by the time it gets to the DCT? It's going to be less sodium because more sodium has been absorbed by the PCT. You see this? So now, as the fluid comes through the DCT, the macula densa is going to sense a certain chemical that it needs to pick up on, sodium. There's less sodium in here. So it acts, macula densa acts as a chemoreceptor. If it senses less sodium here, then that's telling the macula densa the blood pressure must be low. So not only do you have some water in here too, so you have less sodium, more water in here, so the concentration itself, when it gets to the DCT, is very low. So the macula densa acts as a chemoreceptor because it senses less sodium, and it acts as an osmoreceptor because it looks less dilute, or more dilute, or less concentrated. Those two mechanisms are going to tell the macula densa to send what we call paracrines. Ooh, that was taught in endocrinology. Paracrines, something that's going to get released from the macula densa to tell the JG cells, hey, look, I don't know what's going on, but we got less sodium over here, and we got a low concentration over here. Listen, Mr. JG cells, you better be sending out more renin because the blood pressure must be low, and that's the reason why I'm getting less sodium here. So these paracrines get released from the macula densa to tell the JG cells to release renin. Does that make sense? It's a little bit more complicated, but it's going to be asked on the final exam, that concept. Okay? Remember, I've seen the final exam. I know there's questions on it. Does that make sure, do you understand that concept? The monkey, does it help you a little bit? All right? Let me also show you something else here. Let's talk about caffeine. We all know that caffeine, does it make you pee more or pee less? Right, more. You learned that probably in high school. But now you're in A&P. Now you can actually try to understand the concept of why that happens. This is how it works, and it's about the monkey. What caffeine does is that it dilates the sphincters at the afferent arteriole. So it dilates it. If it dilates it, then how much blood is going to go into the capillary? More or less? More. So if you have more blood flow into here, how fast is the GFR? Is the GFR going to increase or decrease? Increase. So now these bananas are going, instead of 60 miles per hour, they're going 100 miles per hour. So how fast do you think this, or let me ask you this monkey, is he able to grab onto a lot of those bananas? No. So what happens here with caffeine, you're going to have a decrease in reabsorption of the PCT. Not 65%, maybe 50%. So that makes for more sodium in here. Does that make sense? So now we got to make sure, so that now the cells over, the macula densa says, whoa, you got a lot of sodium in there. We're not going to tell the JG cells to increase blood pressure. All right? So what happens here is that as sodium goes in here, water is going to stay in there too to keep the concentration up to par. So you're going to have a lot more sodium in here. You're going to have a lot more water in here. So you're going to pee a lot. Does that make sense? All right? That's how caffeine works. I told you about alcohol, now I'm telling you about caffeine. Okay? And this is a big concept when you learn in when you get to nursing, wherever you're going to be taking pharmacology. You ever hear of loop diuretics? All right? Something called Lasix or furosemide. When they're very potent, what we call loop diuretics. They call them loop diuretics because guess where they target? The loop of Henle. All right? They're going to learn about all the diuretics later on. This picture is very important for you guys to know later on. Trust me. Because it's showing you different parts of where diuretics actually attack on here. So that's why it's important to put it on a final exam. That's why it's important that they won't go over it in nursing. They assume you went over the basics of physiology. Okay? So, here's the last piece of the puzzle with what we call the Renin-Angiotensin-Aldosterone Mechanism. All right? This is what's happening here. There's another picture you should really memorize for pharmacology, but for final two. This here is the kidney. It should make sense why I call it a kidney. What it's showing is the Juxtaglomerular Apparatus. There's the DCT, there's the afferent arteriole. So this is what's happening step by step. This is going to sense a decrease in blood pressure. When it does, renin gets released, as we talked about the different mechanisms. When renin gets released from the kidneys, it goes into the bloodstream. So it goes directly into the bloodstream, so because of that, it's a hormone. But it also looks for something called angiotensinogen. Now, if it ends with an O-gin, angiotensinogen, fibrinogen, okay? If it ends with pepsinogen, it's an inactive form. In the presence of renin, angiotensinogen is converted to angiotensin 1. So now renin is a hormone, but it also acts as an enzyme. Now, the angiotensin 1 is still in an intermediate step. It's really not activated yet. It's halfway there. We have another enzyme that comes from the lungs called angiotensin converting enzyme, or better known as ACE. And the angiotensin 1, under the presence of ACE, angiotensin 1 becomes angiotensin 2. Now it's fully activated. Angiotensin 2 is then going to go to the adrenal cortex, and it's going to secrete aldosterone. Aldosterone targets mostly DCT. And what is it going to do? It's going to reabsorb sodium. Water is going to follow. What happens to the blood volume? Increase, okay? Which happens, then what happens to blood pressure? Increases it. All right? You gotta know these steps. Okay? This is a wonderful question for a final exam because look, kidneys, digestive system, respiratory, endocrine. That's the way a final exam should be, to put everything together. It starts off here. This is where it senses things at the DCT, only to go through all these different steps, where the final step of it is that it's going to target DCT. Okay? Any of you heard of a medication called an ACE inhibitor? All right? What an ACE inhibitor is going to do is block this from coming out of the lungs. So you're not going to convert angiotensin 1 to angiotensin 2, which means you're blocking this whole cascade to increase blood pressure. So an ACE inhibitor is going to decrease blood pressure. It's an antihypertensive medication. That's how it works. It's going to block it here. So if you know this and you know that going to pharmacology, you're doing all right. Hopefully you just have to review it, because they are not going to teach it. So that means if you have to relearn it, it's going to be a little bit of a struggle for you. Okay? So just a few things about angiotensin 2. It's going to increase aldosterone secretion. It's also going to vasoconstrict arterioles. And believe it or not, it's going to aid in secreting ADH also. And it increases your thirst mechanism. When you put all these 4 things together, what does that do to blood pressure? It increases blood pressure. That's how angiotensin 2 works. Okay? You could almost see all the following are functions of angiotensin 2 except. Ooh, that could be a question on a lecture exam, right? So this is where you can follow this. It's the same thing, all the different steps of angiotensin 2.